Welcome to the Causal Inference seminar tonight. We're excited to have Kun Zhang from CMU, who will talk about learning and using causal representations. Kun Zhang will stop from time to time to take questions. So please submit them via Q&A. After the talk, we will have a discussion by Cosma Shalizi. And then after that, if we have time left, Kun Zhang will take some more questions. Questions today will be handled by Guillaume. So I'm switching over to him now.
Thank you, Dominic. So as usual, please do submit your questions via the Q&A. There won't be anybody answering them there, but we will select a few of them and ask them to Kun. So if your question is selected, I will ask you to raise your hand and I will unmute you. So please do not raise your hand unless I've asked you to do so. All right, that's it from me. Kun, feel free to start whenever you're ready.
Cool. Thanks a lot. Thanks to the organizers. So I think I can start. Okay, thank you very much, Dominic, Guillaume, Guido, and Michael. So thanks for the organization. And today I'm going to talk about how to learn and use causal representations to improve our approaches to machine learning and AI. So can you see my screen?
Not yet. So you.
Okay, it's going to stop. Yeah. So. So I guess everyone is familiar why we use causality, right? If you want to change something, instead of making passive prediction, you want to use causality instead of association. And a causal view basically can help us understand the phenomenon like symptom paradox, right? We know the associational information is not enough if you want to see what's going on. And also the causal view can help us to understand selection bias. A lot of issues, we have a lot of dependencies caused by selection bias. If you want to go from the biased sample to the population, you have to figure out how the selection procedure was applied and how to do the correction. Okay, good. So let me just give some motivating machine learning examples. So in 2015, Google released the Google Photos photo categorization system application. So you can see right here, the system made very naive mistakes, right? It categorized the African Americans as gorillas. So this is really a very naive mistake. To us, this is a very easy job, right? Why was it so difficult for machines to solve such a simple problem? And after 2.5 years, so Google solved the problem by simply removing the label gorilla from the label set. This is a very naive way to solve the problem. Why is it so hard? Similarly, we know the adversarial vulnerability problem. Essentially, right here, you can see it's a panda. But if you just change some particular pixels in a particular way, or add noise in a particular pattern, all of a sudden, machine will say it's something different, right? To us, it's clearly the same thing. Why do machines have this issue? So basically, we can say that as long as the initial essential feature representation used by the machines is different from what we use, right? This problem can happen because you can always change the input, the raw input, so that the essential representation used by machines or the representation used by human beings become different, right? In either case, it's an adversarial attack. So what is intelligence? Basically, now you can see that as an intelligent system, we expected to not only to deal with the fixed distribution, right? And the intelligent system should have the following capacities. First of all, roughly speaking, the system is able to understand what's going on. I'm not giving a definition of understanding, but at the end of the talk, I'll try to give a rough definition of understanding. Because of the understanding, the machine or the system is able to do control or intervention to achieve a certain goal. And the machine is able to decompose the whole problem or the whole scenario into some simpler modules. And in the reverse direction, the machine is able to integrate the information from different aspects to form a big picture of the problem of the scenario. And also, in light of the understanding and experience, the machine is able to learn with few examples in a new scenario, right? And the machine is able to do not only interpolation, but also extrapolation. So now let me give some examples. Suppose if you play badminton very well, then you can easily learn to play ping pong, and you can quickly play ping pong very well. Why? Because you can decompose the complex skill set into some simpler skills, and then you know how to transfer those skills. As a human driver, right here, even if this is a completely new scenario, you can see the connection between this scenario to the previous ones, and you can make the right decision. But for machines, it's not easy, right? So we can do this kind of extrapolation very easily, but the machine cannot. Why? Here, I'm not giving a concrete way to directly implement or directly achieve intelligence, but I want to provide an alternative way to understand what we mean by intelligence. So here, let's consider intelligence from the evolution and selection perspective. We try to define intelligence and we try to achieve intelligence. Then at least two components are involved right here. First of all, the system is able to survive across almost all scenarios, right? That means the system is able to make good prediction and decision across all scientifically speaking, this will require some inner compact representation of the external world or the environment, right? And second, the machine or the system is expected to be creative. The machine is able to change the environment in some way so that the machine can make a difference, right? Or achieve a certain goal. This will require causal representation of the environment, right? And now you can see the two representations seem to be consistent to some extent. When we were very young, we couldn't really do a lot of interventions to verify causal claims or causal hypotheses. However, we could form some inner compact representation by listening, observing, and analyzing the environment, right? And of course, later we could verify a lot of causal claims. So because of this connection between the two kinds of representation, we have several questions to answer. First, can we just analyze the observed data to derive causal representation? Basically, this is known as causal discovery. I'm giving observational data. I want to do some data analysis so that I can recover the underlying causal structure or the causal model. And second, suppose I know the causal representation of the problem. Can I improve the prediction performance across different scenarios? So basically, this is how we can make use of something like a causal view to improve our performance in transfer learning or domain adaptation. And later you can see how I can address those two issues. So in this talk, I will first talk about how to learn causal representation from observational data. I will start with the traditional constraint-based methods and the functional causal model-based method for causal discovery, which were developed in the last 10 or 12 years. And then I would say something about hidden causal representation learning. This is very important because in many cases, we have a lot of hidden variables involved in the system. And if you want to make good prediction or understand the system in the right way, you have to recover and make use of those hidden variables. And also, I will say something about how to do causal discovery from non-stationary or heterogeneous data. And this is basically because of the coupling relationship or connection between causal modeling and distribution shift. And this would provide the foundation of the connection between machine learning and causality. And finally, I will say something about how to do transfer learning based on the learner representations. You can see the learner representation could represent or could describe some particular property in the data. And this kind of information is really essential if you want to achieve better prediction across scenarios. So here you can see a motivating example for causal discovery. The dataset was collected by my collaborator, Marlene Nobeck, very cool last name. And so she collected 250 skeletons all over the world, and she measured 8 variables. And in archaeology, they really want to understand the causal relation between those features. And clearly right here, you cannot really do interventions. And even if you are able to do interventions, you have to wait very long so that you can see the consequence of interventions. Now we have to do causal discovery from observational data. Why is it possible to do so? Essentially, we have to come up with the connection between causal structure and the statistical information in the data under suitable assumptions. And then we can make use of such a connection to recover the underlying causal structure from data. Basically, this irrelevance information is very, very essential. It says the following thing: if there's no common cause for X and Y, two variables, and right here, I assume X causes Y without the confounder, right? Without a common cause. And then the generation process for the cause X is irrelevant to the process that generates Y from X. So the two modules are not related to each other, right? If you change something here in this process, then there's no reason for anything right here in this process to change accordingly. And sometimes this is known as modularity, right? So now you can see we can, this kind of irrelevance can be used to instantiate different types of independence. For instance, suppose we have Z variable here as a cause of X, then Z, the information of Z will not be useful at all if you want to model Y, given that you already make use of X, right? Because if you want to see something here, you only care about the value of X, but not anything else involved in this process, right? This is implied by modularity. And now you can see this is the conditional independent relationship between Z here and Y given X. This is conditional independence enforced by this modularity condition of a causal system. So traditional causal discovery method like PC and FCI methods make use of this kind of conditional independent relations in the data. Basically, this is how the PC algorithm, Peter-Clark algorithm, works. So we have data right here. From data, we can discover a set of independence or conditional independent relations. And at the same time, we start from a complete graph in which each pair of the variables is adjacent. And if two variables are conditionally independent, given anything, then they are not adjacent. Okay, this is because causal Markov condition and faithfulness assumption we just assume here. So faithfulness assumption said that any conditional independent relationship in the data is a reflection of the information of the structure. So if they are conditionally independent, they are deseparated according to the graph. Now you can see since 1 and 5 are conditionally independent given 3, we don't have this edge. And since x2 and x4 are conditionally independent given x1, we know 2 and 4 are not adjacent and so on. So now you can see, oh, we have the skeleton, undirected graph. And then we can discover the so-called V structure. Right here, you can see x2 and x4 are conditionally independent given x1, but not a subset of variables containing x3. Then we know right here, we have a V structure. The causal directions must go from x2 and x4 to x3. So we have those directions. This is the V structure. And also we can do orientation propagation. Right here, you can see the causal direction between x3 and x5 cannot go this way, because if it goes this way, we will have a fake V structure, right? It's not possible. So the causal direction must go this way. And we cannot determine the direction between x1 and x2 and the direction between x1 and x4. That's it. We end up with the so-called Markov equivalent class. All decks in this class will have the same set of conditional independent relations. Okay, so this is how the PC algorithm works. Now you may have two questions. First, right here, we assume there are no confounder or hidden common cause for two variables in the system. What if you have confounders? Can you deal with confounders? Can you say anything about the confounders? Second, you can see in this result, for some of the edges, we cannot determine the causal direction, right? So is there a method to determine all the directions in the causal graph, right? If we have such a method, basically we can estimate the underlying causal graph, directed graph uniquely. Is it possible to do so? I will address those two issues. So first, let's see how we can deal with the confounders by making use of only conditional independent relations. Let me just give two examples. In the first example, basically 1, 2, variable 1 and 2 are independent, 1 and 4 independent given 3, and 2 and 4 independent given 3. If you apply the PC algorithm, you end up with this. We say, oh, here we have a V structure, and here we know we can determine direction because of this structure, and here we determine direction because of orientation propagation. Do you think it is possible at all to have a confounder behind X3 and X4? Is it possible to have this hidden variable C right here? So under the Markov condition and faithfulness assumption, we'll say it's not possible. Why? Because if you have a confounder here, then this path will be open if you condition on X3, meaning that X1 and X4 will not be conditionally independent given X3, right? As a consequence, since we know X1 and X4 are conditionally independent given 3, this is not possible, meaning that it's not possible to have this confounder right here. So in this case, we are sure that there are no confounder, and we are further sure that X3 is a direct cause of X4. This is cool. And here I give a daily life example. You may have a look at this example later. So we can make use of this method to infer causal information even in our daily life. Now let's look at another example. So here, variable 1 and variable 3 are independent. 1 and 4 are independent, 3 and 4 are independent. If you apply PCR algorithm, you can see something interesting. So they are adjacent, and 2 and 4 are supposed to be adjacent, but since 1 and 4 are independent, we know, oh, here we should have a V structure. And we also know that 2 and 3 are independent. Then we should have another V structure. Right here, we see conflict, right? This is the conflict. We can see the conflict in the orientations. What happened? This just means that, oh, right here, we have to introduce some latent variable to explain the dependency between X2 and X4. And furthermore, we know that it is not possible at all to have direct causal relation between X2 and X4. So in this case, we can infer there must be confounders for this pair of variables, and we are sure that those two variables are not directly causally related. Neither of them is the cause of the other. You can also see some other examples. So basically, here you can see very general ideas that can be used to infer whether there could be some confounders behind some pairs of variables by making use of only the conditional independent relations in the data. So for details, maybe you want to have a look at the FCI fast causal inference algorithm. Basically, such information or such ideas are incorporated in FCI algorithm. Okay, and then still you cannot determine the orientations of all edges, right? Is it possible for us to determine the causal edges? Okay, I will stop here to take questions.
Thanks, Kun. So there are two questions. One is a clarification on the kind of concrete example that you discussed about basically what are the 8 variables that you're interested in. The second question is perhaps more general to causal discovery, and it's about how much should you trust the conditional independence tests that are used when that are kind of like the building blocks of these PC and other such causal discovery algorithms.
Cool. Thank you very much. Very good one. So here, I shouldn't have skipped this slide. So right here, you can see the 8 variables. They include the gender, cranial size, diet, the location, climate, cranial shape differentiation right here, and level of attrition in teeth, and some other behavior. So basically, they want to understand why people from different areas look different, right? And also, they want to make prediction into the future. So this is the result produced by PC algorithm and the kernel-based conditional independent test method. So basically, right here, you can see we have 8 variables, and some of those edges are directed, given by PC, and some of them are not directed. If you introduce some background information, which is that the climate shouldn't influence location, then given this edge, we can do orientation propagation, then we can find a whole directed secret graph. And right here, basically the information is consistent with domain knowledge in archaeology, and we still find something new. For instance, here, we can see diet is a cause of cranial shape differentiation right here. Basically means what you eat will change how you look. So, but at the same time, we know that this influence is not direct. It takes place via another two variables. If you just want to use domain knowledge, it's really hard to find such information. Really hard to distinguish between direct and indirect causal influences. Okay, so basically we have 8 variables here. I hope this answers the question. And now regarding the second one, so how many can you trust the conditional intent test when building your DEX? This is a very good one. That's why a lot of people are still working on conditional independent testing methods. Very important. And in practice, you may have type 1 and type 2 errors, right? So it's complicated. I would say it really depends on how many data points you have. If you have enough data points, type 2 error is very small, and you can use a very small value for alpha, so that the type 1 error is very small, and finally you can have a very nice bound on the error. Otherwise, if you have few data points, probably you have to usually you have to try to reduce the model class or space so that you can find more convincing causal discovery results. So it's a very important problem, and probably better conditional intent testing method will be proposed in the future so that we can further reduce the error. In practice, if you have, say, 200 variables, in the linear case, the error would be relatively small, but in nonlinear cases, maybe you want to make use of, say, 300, 500, even more data points to get something very plausible. Okay, so this is very empirical, and I hope this could at least give you some hints as to how to apply those methods on real data.
Yeah, that makes sense. Thank you, Kun.
Okay, great. Thank you. Let me just go ahead. So how can we determine the underlying causal graph uniquely? Right here, you can see in the linear case, if you assume the knowledge terms are non-Gaussian, we can break this symmetry between the two variables, and later I will give a clearer picture. And similarly, post-nonlinear causal model and additive knowledge model were proposed. And for all those models, we can really distinguish between cause and effect. As a consequence, we can find a causal asymmetry between two variables, and we can also recover the underlying DAG uniquely. So right here, you can see how we can go from linear correlation or correlation to causal asymmetry in the linear case. So in the first, in the top panels, I consider the Gaussian case where the cause X and the knowledge term E are Gaussian. And I generated X first, and then I generated Y. In other words, X caused Y, right? So if you try to explain X with Y with X by linear regression, you can see this is a scatter plot of the residual and X. They are uncorrelated and further independent, because this is just a way to recover the underlying true process. And if you switch X and Y and do linear regression, you can see again the residual will be uncorrelated from X and also independent from Y. So the residual will be uncorrelated from and independent from Y, because in the Gaussian case, independence is equivalent to zero correlation. And then at the bottom, you can see another situation where X and the knowledge term E are uniform instead of Gaussian. Now you can see if you try to explain Y with X by linear regression, the residual is independent from X, right? This is just a way to recover the true process. And if you regress X on Y this way, you can see the residual will still be uncorrelated from Y, right? By construction, regression residual is uncorrelated from the predictor. However, they are clearly dependent, as you can see from the scatter plot. You can see the conditional distribution of a second variable EX given the first variable Y is very sensitive to the value of Y, so they are not independent. Now you can see the causal asymmetry in the linear non-Gaussian case. And this idea can be extended to handle many variables. And this model is known as the linear non-Gaussian acyclic model. And later, we extended this model to incorporate nonlinear functions. And we try to make this model very general so that it can finally approximate the true generating process. And secondly, it's really important to guarantee the asymmetry of the between the two variables, cause and effect. Because without this identifiability of a causal direction, we cannot distinguish between cause and effect. We cannot recover the underlying causal graph. We may not be able to recover the underlying causal graph uniquely. And we believe that at least the three effects should be considered in this model. Right here, we have causes, and the causes may have nonlinear effect, as you can see from here. And furthermore, we have noise right here. And in many cases, we have sensor or measurement distortion. Putting them together, we have the post-nonlinear causal model with inner additive noise, as you can see from here. And this model contains a linear model, nonlinear additive model as special cases, right? If you set both of them to linear functions, linear. And if you set fi2 to linear function, then this is a nonlinear function with additive noise. And even if the noise is a multiplicative instead of additive, you can see it's a special case of this model, right? As you can see from this comparison. So this model is rather general, this model class. And right here, you can see how we can distinguish between cause and effect with this model. We assume x1 causes x2 right here. We are giving only the data, right, for x1 and x2, two variables without any temporal information. So first, we assume x1 causes x2. We fit the model, we estimate nonlinear functions and the noise term. You can see the noise term is basically independent from the hypothetical cause, which is x1. And then we switch x1, x2, assuming x2 causes x1 instead. We fit the model, estimate the nonlinear functions and the noise term. And now you can see the noise term is not independent from the hypothetical cause, which is x2. Then we can say, according to this model, x1 causes x2. And for the other direction, we cannot find the independent noise term. Actually, x1 and x2 are the altitude and temperature of more than 300 cities in Germany. So x1 should be the cause of x2, not the other way around. And then now empirically, we can use this kind of structurally constrained functional causal model to distinguish between cause and effect and recover the underlying causal graph uniquely. And we should give some theoretical guarantee. So right here, you can see after some derivation, we can just figure out all those situations in which cause and effect are symmetric. So with this model, even for the reverse direction, we can still find the independent error term. In total, there are only 5 situations. The first one is very well known. It's a linear Gaussian case. So in the linear Gaussian case, we know that the causal asymmetry just disappears. And basically, all those 5 situations are very specific. You have to tune the nonlinear functions and the distribution of the noise terms very carefully so that one of them holds true, right? In other words, generally speaking, causal direction is identifiable even for the data generated according to this very general model, right, with 2 nonlinear functions. And this model class contains linear models and the nonlinear additive noise model as special cases. This identifiability result will also apply to the linear models and nonlinear additive noise models. And generally speaking, we can recover a causal direction between 2 variables if this mild assumption holds true. This is how we can discover the underlying causal graph uniquely by making use of further assumptions, rather mild assumptions on the causal mechanism. And of course, given this, you can also infer whether there are confounders behind a pair of variables, because we know that if they're the confounder, then you can easily show that for neither of the directions, you can find the independent error term or independent noise term. That's why you can still infer whether there are confounders behind each pair of variables. Okay, so right here you just saw some fundamental method for causal discovery, and now let me say something about the practical issues in causal discovery. So in practice, we may have various kinds of nonlinearities, right? And we can have discretized values, as you can see from here, categorical variables, and even mixed categorical and continuous variables in the data set. We have to deal with such a situation. And very often times we have measurement error, right? What you measure might be different from what you want to measure. And in some cases, you don't even know how to measure the underlying true variable. You don't know what the underlying true variable is. You have to find a proxy or surrogate to see what's going on. This way you can see the measured value might be different from the true value. And in some cases, we may have uncertainty in the data, measure the data. So we have to deal with those issues in order to recover the true graph over the true underlying variables. And we have selection bias in many cases, right? If you work with the data collected on the internet, you always have selection bias. So you can see how you can recover the underlying true causal graph and true functional causal model, even if you have a different kind of selection bias. And confounding is a big issue in causal discovery. First of all, you want to see how you can discover the true causality among the measured variables in the presence of confounders, right? So even if there are confounders, I can still infer the causal relation between the measured variables. And more importantly, in many cases, you can see the measured variables are actually reflections of the underlying hidden causal variables, which are causally related. So in this case, you want to recover not only the confounders, but also how the confounders or confounding variables or high-level variables are causally related. I will say something about this problem in a few minutes. And in many cases, especially in healthcare, we have missing values, right? You can see how missing values, the issue of missing values can be dealt with for causal discovery. Basically, you can just need to do some correction in order to recover the true causal graph if you have enough data. And causality in time series is a traditional problem, right? We want to discover causality from time series. However, dealing with time series might be very complicated because the resolution can be very different from the true causal frequency. And in many cases, we only observe part of some of the processes that interact with each other. So right here, by further leveraging the temporal information, we can recover time-delayed causal relations and instantaneous causal relations, and you can recover the true causal influences, temporal causal influences from low-resolution data. The low-resolution data may be aggregated data or subsample data. Basically, for both kinds of data, both aggregated data and subsample data, in theory, you can still recover the true temporal causal relations from such data. And you can recover the true causality among those measured processes, even if you have some hidden processes interacting with those processes. And very oftentimes we have non-stationary data or heterogeneous data. So we can actually learn causality in a more direct way because of the relationship between causal models and the distribution shift. I will say something about it later. Now, let me have a look. So I will take questions in probably 6 minutes after finishing this part. Now, let's see how we can learn hidden causal representations. So the problem definition is as follows. Right here, we are given data set. We have measured variables xi's, but the measured variables were generated by hidden variables. Those hidden variables may be causally related. So what we observe is just a reflection of the underlying process. And we want to recover the underlying hidden variables together with their causal relations. And you can see in many cases, we want to solve this problem. For instance, we do not believe that the answer scores in psychometric questionnaires are causally related to each other, right? Instead, they were generated by the hidden mental conditions, and the mental conditions can be causally related. So we want to understand the underlying mental condition and their relations by analyzing the answer scores in psychometric questionnaires. So this is the problem. So now can we just recover the hidden world involving LIs and their causal relations by analyzing those measured variables? So under some assumptions, this is doable. Let me introduce the independent noise condition first. So independent noise condition is very simple. So we say ZY follow the independent noise condition is the regression residual of regressing Y on Z is independent from Z. And this way, in the linear non-Gaussian secret causal model, we can determine the causal ordering and further determine the whole causal graph by making use of sparsity constraint. And right here, if Z is the cause of Y without the confounder, then this condition holds true. Otherwise, this condition will not hold true. So we can easily determine the causal order between X2 and X4, and the causal order between X2 and X1, and between 2 and 4, and so on. And finally, we can find the whole causal order of the variables, and then you do regression with sparsity constraint, you can recover the whole causal graph, right? So this is rather simple. It's just about whether the regression residual is independent from the predictors. we define the.
Sorry to interrupt. You have around 10 minutes left. Just a reminder.
Oh, sure. And right here, now you can see, we propose that linear non-Gaussian latent variable called the model. Right here, the noise from the non-Gaussian. We have hidden variable and embedded variables, and we propose a generalized independent noise condition. This way, this is a generalization of the previous independent noise condition, but with this condition, essentially we can verify whether specifically some specific linear combinations of the variables are independent from each other. As a consequence, we can first find the causal clusters. A cluster is a set of variables sharing the same latent variables as the parents. So we can find the clusters, and furthermore, we can determine causal order of the latent variables. Now we can basically recover everything, and if needed, you can determine all those coefficients. Okay, so with the general independent condition, we can recover the hidden world. This application, so we analyze the teacher burnout data set. Right here, we have 28 measured variables, and we recover the hidden variables right here, and also the causal asymmetry or causal ordering of the hidden variables. And our result is almost identical to the hypothesized model given by the experts. So this verifies the usefulness of this computational method, and also illustrates that the hypothesized model by experts is very reasonable. And then in many cases, we have non-stationary time series or heterogeneous data sets. If you collect data under different conditions, the data distribution may be different, right? So here we just leverage the connection between causal models and differential shift. It's because if you have a right causal model, then distribution of the cause and distribution of the effect given the cause may change, but they change independently. And then you can see in this setting, some causal connections, some causal inference may be larger in some scenario, and some of them may be weaker, and some of them may even vanish in some scenarios. And this proposed framework, we can solve the following problems. First, we can identify those variables with changing causal mechanisms. So right here, we know, oh, for those variables, the mechanism changes, and we can determine the right causal skeleton. And furthermore, by leveraging the property of independent changes given by the causal system, we can find the causal direction easily. And finally, we can do a so-called kernel non-stationarity visualization to visualize the driving force of the change in the causal mechanism represented by the conditional distribution. And here you can see application. So we analyze the major stocks in New York Stock Exchange. We use the daily returns. So here you can see we find not only a graph, but also direct graph, right? And we can visualize the estimated driving force of non-stationarity in the causal mechanism, as you can see from here. This is 2008, where financial crisis happened. You can see in 2007, the risk was already very high. So we basically here, we discover everything, including causal graph and the underlying driving force of non-stationarity by analyzing only the daily returns. And yeah, now let me spend 2 minutes on questions.
Yeah, so maybe we'll keep that short so you have time to finish your talk. So some questions that are recurrent are about the practicality. And so one is how sensitive the different methods that you propose will be to model misspecification. You brushed a little bit on that, but there were some questions about that. And other questions are about how do you determine in a specific instance what kind of sample size you will need based on, say, the dimension of your problem?
Oh, very good ones. So they are very practical, important issues. And I think there are some papers on, say, false discovery rate of causal discovery methods, right? Given the sample size and the alpha level, significance level. And I would say you can easily check literature by searching false discovery rate, right? Error control in causal discovery. But basically, I don't think there's a kind of unified way to answer the question, because it really depends on what method you use for conditional inference test, what method you use for independent test in functional causal model-based method. So it's you may, if you want to use a particular method, I would say try to find some papers in the literature, and also maybe want to do simulations to see how certain the conclusion, the discovered causal graph is. Oh, this is just a short answer. Should I just continue?
Yeah, that makes sense. Thanks. Yeah, please continue.
Thank you. Yeah. Now let's have a look at some machine learning problem. Specifically here, let's look at domain adaptation problem. So in traditional machine learning, we assume the training set and the test set have the same distribution. In practice, you may have different distribution across different data sets. So here we have some source domains and one target domain. In the source domain, we have x, y values, y is the variable we want to predict. And in the target domain, we want to predict y from x. Now we can see if you want to solve the problem, you have to find a way to connect different distributions or different scenarios. That means you have to find some high-level representation. And this representation will be a bridge so that you can jump from one scenario to another to make prediction. And with this example, I want to illustrate that causality may matter if you want to make prediction, especially in non-stationary environments. So in this example, suppose this is me. First question, if you see my shadow, can you say anything about my figure, right? Can you even say something about the environment? Suppose we basically, this is a new scenario. Now you can say, oh, I can say something about your figure. I can even say where the light is from. But if you just see my figure, can you say anything about my shadow? You don't know how long it is. You don't know in which direction it is, right? So basically, predicting cause from effect is easier in non-stationary environments. Why? Because in any case, the effect already contains the information of the cause. We just want to make use of some additional constraints we learned from experience to separate the contribution from the cause and the contribution from the environment, right? In this way, we can just recover the cause information from the effect. Okay, in light of this intuition, we propose the model for domain adaptation. So in many cases, the y, the variable we want to predict, is actually the cause of the features. So this is target shift, and this is conditional shift, and this is generalized target shift. Basically, in light of the previous intuition, we can solve those problems relatively easily because we can recover the joint distribution of x, y from only the distribution of x in the target domain. However, you may want to go further. If you are given data set, how can we develop some end-to-end framework to do domain adaptation? We can automatically discover the property of the data and make use of the property, right? So this also invited another question. Do we always need to go to the causal level if you want to do domain adaptation? The answer is no, right? Because if you want to make prediction across scenarios, you just want to find those stable information, stable properties of the distribution that can be used. And it's much harder to find the causal information. Usually, if you want to find the causality, you have to assume something rather strong. And just think of the classical conditioning example. Right here, the dog can make very good prediction across scenarios, right? Because dogs just make use of very stable associational information. We can do something similar. So this is the approach to data-driven domain adaptation. Here, we are given different data sets. And from data sets, by making use of the method of causal discovery from non-stationary or heterogeneous data, we can discover a representation of the changeability of the distribution across scenarios. So if you have a theta variable here, it just means the conditional distribution of this variable given the parents may change across domains. And this provides a compact representation of how the distribution may change across domains. And also those theta variables are independent. So we have independent modules. And of course, if there are no theta variable into this guy, it just means that the conditional distribution of this variable given the parents is invariant across scenarios. And finally, domain adaptation is nothing but a problem of inference, Bayesian inference on this graphical model, given the values of the features in the target domain. So this provides a principal way to understand and solve the problem of domain adaptation. And here you can see some results on simulated and real data by this method. In the first table is the result on simulated data. Basically, you can see the last column is the accuracy given by our method. So compared to all the alternative methods, this new method gained quite a lot in the prediction accuracy. You can see there's a very big improvement, right? The accuracy goes from 70-something to 80-something, and from 80-something to 90-something. So basically, why do we have this benefit? It's because the model is very flexible to capture the property of the data. And at the same time, we can discover such information automatically from data. And finally, let me say something about.
Sorry to interrupt. Can you wrap up in 2 minutes or so? Because the discussion.
Oh, yeah, sure. Just 1 minute. 1 minute would be enough. This is the last one.
Yeah. Sorry.
Cool. So, yeah, basically, if you want to make use of different scenarios and different tasks, you want to find a unified compact representation of the world, right? This representation can connect different scenarios and different tasks. And we can learn this representation from different scenarios, which may have the same or different variable sets and different conditional distributions by making use of independent and minimal changes across the scenarios. And furthermore, with further assumptions, this representation has a causal interpretation. So those relations will be causal. And of course, in some scenarios, say if you want to solve the problem of reinforcement learning, maybe you want to introduce dynamic properties, right? And you also want to introduce selection bias, because optimization basically is a way to do selection. So the point is that if you learn this unified representation, then you can solve many problems in a unified way, in a principled way. Okay, finally, to summarize, we can use different types of independence to discover the causal structure from data. So with the conditional independent relations, we can develop a constraint-based method. This will recover the Markov equivalence class of the underlying causal graph. And with the independent noise condition, together with the constraint functional causal model, we can find a causal asymmetry between two variables. And as a consequence, we can recover the underlying causal graph uniquely. And if you have non-stationarity or heterogeneity in the data, you can further make use of independent changes of the causal mechanisms, and then you can recover more information. And finally, I want to remark that a number of machine learning problems may benefit from this kind of representation, causal representation or causality-related representation, because this representation provides a compact description of the distribution change across scenarios, and also it describes the property behind the data. This way, you can go beyond the data to make better prediction or to realize what's going on right there and make use of such a property. Okay, finally, I want to thank my collaborators, including Biwei Huang, Mingming Gong, Bernard Sharkov, Apple, Clark, and Peter, and others. And this is, as you can see, the Causality group at CMU. Thank you very much.
All right, thank you very much, Kun, for the very nice talk. We're now switching over to the discussion. So we'll have Cosma Shalizi present some slides, and after that, Kun, you will have the opportunity to quickly respond.
Yeah,
so,
thank you.
Cosma, whenever you're ready.
Okay. All right. So hopefully everyone can see my slides.
Yep.
Yep, great. So I want to echo Guido's thanks to Kun for the very nice presentation. Kun has laid out very clearly the importance of the kind of work he's talking about for issues in machine learning and AI. As someone who's more or less a statistician, I wanted to talk about the sort of statistical viewpoint and the statistical big picture of the work he's discussing. And hopefully this will actually also give another way of addressing some of the issues which came up a bit in the questions during Kun's presentation. So I want to step back a little bit and sort of orient us all by distinguishing two key problems in causal inference. One is what we might roughly call estimation problems, where we say we're going to assume a certain causal structure. If we've listened to Uncle Judea, this is a DAG. If we like non-parametric structural equations, it's a non-parametric structural equation. If we've listened to Uncle Don, it's some ignorability assumptions. We make some structural assumptions, and then we ask, if we set some variables to certain configurations, what's going to follow? Or we do Bayes' rule to invert that. But we're assuming certain causal structure. And then there's the discovery problem. What is this right causal structure anyway? How do we figure that out? And estimation problems, under which I include like policy learning and learning a treatment regime, these are, we have now figured out how to make these fairly standard statistical problems. We have to be very clear about the estimand, about what exactly we are trying to estimate. We have to be clear about, under what conditions or under what assumptions is the estimand identified from the distribution of what we can directly observe, right? When is the estimand a function of the distribution of observables? And then we have to get very clever about the statistical inference, because we have figured out some observable function, statistical functional, which tracks our estimand, and we have to get some good way of estimating that, or doing hypothesis testing, or all the other conventional ordinary statistical problems. So that's what most of the seminar is about. That's what this huge literature is about. That's what most of us spend most of our time on. And I don't mean to diminish it in any way. It is an immense and extremely important task, but all of it, in any one of these problems, the starting point is assumptions about causal structure, about the DAG, or about ignorability, and so forth. And so that sort of logically pushes us back to a previous question, which is, we see some distribution over observables, or we have limited data, so we have a sample from the distribution over observables. What is the causal structure lurking out there in the world behind the observables which produced it? And that is what Kun is focused on. That is what Kun's entire presentation is about. And I'm going to, for brevity, say the causal structure. It is entirely possible that there, even with perfect information, we would only be able to say some range of causal structures. There are, we might not have point identification. We may only have partial identification of the causal structure, the same way that sometimes we only have, partial identification of various causal estimands in conventional estimation problems. And, obviously experimentation is one way of answering this. It's sort of the ideal way of we have been doing 3+ years, and it's taught us a lot, and we would like to do it. But it would be really nice if it's not the only way of discovering causal structure, because lots of things we think are sciences just do not rest on experiment in any of the ordinary senses. When geologists tell us how earthquakes arise from tectonic plates rubbing against each other, they do not go out and do randomized controlled trials where they jiggle the tectonic plates. The people in the geology department at Stanford are not going out to the San Andreas Fault and moving one side of it on a randomized schedule to confirm that, yes, it causes earthquakes. So there have got, it is possible that we're just fooling ourselves and the geologists do not actually understand what causes earthquakes. I am open to this possibility, but my sort of conviction is that they probably do understand that. There is probably some way of doing causal inference which doesn't rest on randomized controlled trials or experimental intervention. And it would be nice if we could systemize that and algorithmatize that and do some statistics with it. So let's just think a little bit about why we think discovery problems are solvable. Well, the obvious answer is that they're not solvable. Okay. And this is classic stuff. This really does go back to Hume. Said all you can actually observe is an association between events or association between variables. You just can't observe counterfactuals. It's kind of there in the definition. And you cannot actually observe any kind of necessary connection. You can only observe constant conjunction. And all that's observable is association, not causation. And I think I have time to do this. He was actually anticipated on this by a couple hundred years by a great Muslim philosopher and theologian Al-Ghazali, who wrote this wonderful attack on causality, where he's, part of his argument is saying, look, it's not habitual for a corpse to sit up in its coffin and write a book with excellent handwriting, but habits can change. There's nothing logically impossible in this, nothing that our previous observations would rule out. This could always happen. So, it's basically the same kind of argument Hume is making. It's basically correct. There is no way around it as a matter of pure logic. Lots of people have tried to find ways around it as a matter of pure logic. And as Bertrand Russell says, there's a special place in hell for them. They are just not going, anyone who thinks they have refuted Hume or Al-Ghazali on this is just wrong. So, I want to ask, is Kun putting his soul in danger? Is Kun in danger of winding up in this special section of hell? And I don't think so. I think Kun can take a deep breath. And the reason is that we are imposing some causal assumptions. Okay, Kun is not claiming to make causal conclusions out of nothing, out of merely statistical assumptions. Kun is starting from some causal assumptions, but ideally, if we're going to do this kind of discovery, they should be weaker and hopefully more plausible than the assumptions we use to do estimation problems. Right, so that if you're willing to buy the assumption for an estimation problem, you should also then be willing to buy it for the discovery problem. And because we've got causal assumptions going in, we can get causal conclusions out. And, you know, as usual, if we make the assumption stronger, you're going to get stronger conclusions. That is logic. That's also our life as statisticians. But we are making hopefully weak, qualitative, plausible assumptions. And the magic will be if we get precise conclusions out of that. And there's this wonderful line from Freud that the goal of therapy is to turn neurotic misery into everyday unhappiness. And so here, the goal of causal discovery is to turn what seems like this miserable philosophical problem of how is the world actually structured behind what we can see into everyday statistical unhappiness. We have a big optimization problem, and how do we solve it? And how stable is the answer to small perturbations of the data, and blah, 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 blah. But this is the goal. We want to turn causal discovery into an everyday statistical problem. So we have a familiar sort of unhappiness. And it's a special kind of statistical problem. It's a distinct kind of statistical problem from where you're thinking about when we're estimating particular rationals. That's because causal structure is qualitative. So, it is this DAG or whatever the other equivalent under a favorite causal formalism is, and not this other DAG. And the DAGs are not continuously deformable into each other. There's no continuity on that space of causal graphs. So picking qualitative aspects to a statistical model is model selection. Right? The same way that you have to decide these variables are going into my regression and not others, that is a qualitative structure problem. That is what we do with model selection. And we understand a lot about model selection. Okay, so what we are asking for is to do model selection on a particular class of models where we make certain assumptions about what those models represent. And if we can do model selection in a consistent, reliable way, then we have at least some hope of doing causal discovery in a consistent, reliable way. Now, there are a lot of issues which arise in model selection in the statistical theory, which are different from what we're used to in just ordinary parameter estimation. Because it's qualitative, you can't just take a Taylor series to second order, throw away everything else and solve, which is most of parameter estimation theory. There are things like, there can be trade-offs about, how much of a penalty do you need to impose, how much data do you need, and so forth. But these are fairly well understood statistical issues. Okay? These are things which we have studied as statistical problems for a long time. That is what we are doing in causal model discovery. There's a bunch of questions about during the chat actually about how much uncertainty is there, and I want to say this is a problem with post-selection inference. Right? If we are using the same data to discover the model structure, and then we want to estimate some effects within that discovered structure, fine, we're doing post-selection inference. We know that it's going to distort things, and we can either do heroic efforts to correct for post-selection inference and do that, do things very carefully, or we can just do data splitting if we are willing to assume independent samples, and you get almost the same answer. But it's a problem of post-selection inference. And there are issues about what is the distribution of models that you will select. Again, those are things where we have some statistical handle on it from the theory of model selection. And of course, model selection always rests on some assumptions. Different procedures are going to be appropriate, are going to be consistent under different settings, under different assumptions about the statistical process, about what kind of qualitative structure you're dealing with. But This is a familiar statistical problem of model selection. So what kind of results do we get in causal discovery? What kind of results does did Kun just lean out for us? When she say, look, if you make these qualitative assumptions about causal structure, and you add on some further assumptions about the sort of purely statistical parts, essentially what is the relationship of each variable to its parents, that kind of thing, like his noise assumptions. Then, as a provable thing, this procedure or that procedure will consistently, with probability tending to 1, select the right causal structure, or it will select a causal structure which contains in a set which contains the right one, because sometimes we only get the equivalence class. Sometimes we don't have point identification of the right structure. But these are basically model selection consistency results. Model selection consistency is a thing. It is not an outrageous thing. It is not a thing we think is impossible. If you're willing to make these assumptions, some of them qualitative and causal, some of them more conventionally statistical and sort of functional formy, then we get results about consistency. And he talked about constraint-based methods. He talked about noise-based assumptions. He talked about the very interesting work he's doing about hidden variables. And this is all just saying, okay, if you're willing to make these assumptions, these conclusions follow. These selection procedures they are going to consistently deliver the right model structure. So we get back to the issue about buying assumptions, about what assumptions we are willing to accept. And this is something where we need some knowledge of the world, and we also, frankly, have some amount of personal bias and prejudice. Because I was trained, whenever I see a linear model, it is incredibly hard for me to accept that as anything more than a very local Taylor series approximation. But I recognize that this is a statement about my personal prejudices, and also potentially something at least about linearity that we could investigate. The art or goal in the causal discovery world is to expand these assumptions so that we get more and more situations where we know under these assumptions these procedures will work. And as we can expand that range of assumptions where we have consistent discovery procedures, it should be easier for more and more people to accept these kinds of results without straining your conscience. Now, there will inevitably be some sort of identification possibility frontier where at some point we've maxed out our procedures, and the only way to get a more precise conclusion from the same data set is going to be to make stronger and therefore more expensive or harder to swallow assumptions. Kun modestly did not talk about the very interesting work he's done about non-parametric conditional independence tests, which give you a way of doing the kind of classical constraint-based causal discovery for very, very general sets of variables. They've got lower power than partial correlation tests for conditional independence, which assume everything is linear and Gaussian. Okay, that's a fact, and we might wish it away, but it is a fact. But this is not a specific problem to causal discovery. Any sort of data analysis problem, especially any sort of identification problem, the stronger the assumptions you're going to make, the more things you're willing to exclude a priori, the stronger the conclusions you're going to deliver. And Chuck Manski has been preaching this sermon for many decades very eloquently, and I will refer you to him rather than trying to better that. But this is, again, an ordinary statistical problem. It is an ordinary everyday source of statistical unhappiness. It is not something unique to causal discovery. It is certainly not even something unique to model selection. Speaking personally, I would say that if any among us has ever estimated an average treatment effect by propensity score matching, then we've said, what kind of assumptions are we willing to buy and defend in public? And so we've established the price at which we are willing to be bought. And I will, many of the procedures that Kun talked about rest on assumptions which are substantially weaker or certainly comparable to the assumptions you would need to say that this average treatment effect is identified and estimable by propensity score matching. I've certainly done that. I've provided people results saying, yes, here's propensity score matching estimate of an average treatment effect. I am not trying to say no one should use propensity score matching to estimate average treatment effects and defend those estimates in public. I am saying if we're willing to do that, then I don't understand why you'd be willing to make those assumptions, accept those assumptions in that setting, but not carry over those assumptions to these discovery procedures. So let me just sum up. Okay, we know there are actual theorems that we can do causal discovery under some combinations of causal and statistical assumptions. Many of those combinations of assumptions are weaker than ones which we conventionally accept for causal estimation problems. So I think we should, this is something where we should just press ahead. As statisticians, we should think of this as a model selection problem, a particular kind of model selection problem where we're dealing with selecting among models with certain qualitative features like the DAGs, potentially including many latent variables, but it's a selection problem. And we should begin applying the technology, or we should continue applying the technology we have developed for model selection. And I think there is a huge field here for statistical and econometric work. If a lot of the time our conclusions are not going to be very precise, if our confidence set over possible causal structures is going to be large, that is telling us what we need to investigate, and it should be giving us considerably wider margins of error and humility when we then go and do things like estimate treatment effects within each model. This is a direction we should really be pressing ahead with. So thank you very much to the organizers. Thank you very much to Kun. And now I'm afraid I'm actually 10 minutes late for my next meeting. So I am having said all these provocative things and threatened everyone with perdition. I'm afraid I need to leave. But I will be sharing the slides with the organizers, and I will be happy to continue this discussion by email at a later date.
Yeah, thank you so much, Cosma. Thanks.
Thank you, Cosma.
Yeah, we're also slowly running out of time, but I think it would still be interesting. Kun, do you want to quickly respond to the discussion?
Yes, actually, let me just answer the questions right now.
Okay.
To save time, maybe you don't have to read. Yeah, do you want to read the questions first?
We can do that. Is there a particular one that you wanna?
No, maybe I can just give a quick response in order, right?
Okay,
let me see. So in the regression, let me, because I also need to leave to teach. If the regression uses a misspecified model, is the independent noise condition not able to check whether there's a confounder? Yes, that's right. If the relationships are nonlinear, right? But you use linear regression, then clearly you are not going to end up with independent noise. That's right. So in this case, you can first check for linearity assumption, and if it holds true, you can go further. Otherwise, you should try to use a broader model class. Next question, looks like logged data snooping to arrive at a satisfactory model. If that's right, how do you justify efforts to represent uncertainty? Select test. Oh, that's really, I don't know specifically what you mean by justifying efforts to represent uncertainty, e.g. statistical tests. So maybe someone can say something about it. But before that, let me respond to last question. Can you talk about how the uncertainty about the graphical model specification affect the performance of the model? This is a really good one. So basically, we always have to assume something. This was also pointed out by Cosma. And right in the last work, basically we assume that the model distribution, right? Something is invariant. That representation is invariant. Otherwise, you have to go to a higher level to capture the information or property of the data. So if this is the case, if you find that this model, this graphical representation together with the prior distribution for those variables, additional root variables, then you have to go to another level. You have to find a more flexible one, right? That covers this particular one as a special case. So basically, this is how we deal with uncertainty. You have to find the invariance or some constraints in the uncertain data, and then you can discover and make use of the constraints underlying uncertainty. Okay, regarding justifying efforts to represent uncertainty, e.g. statistical tests, can you say anything?
Sorry, can you say again?
Oh, that basically says, how do you justify efforts to represent uncertainty, e.g. statistical tests? So probably it means the uncertainty, how the uncertainty in the conclusion given by statistical tests will affect the quality of a causal discovery, right? I don't know precisely what it means.
Yeah, I think we're now also really running out of time, so I think we
okay.
should,
So
wrap up soon. Yeah, thank you very much. We're going to send you a copy of the questions.
Yeah.
In any case,
maybe
yeah.
we can discuss those by email. Thank you so much.
Yeah. First of all, yeah, thank you so much, Kun Zhang, for a very nice presentation, and also Cosma, even though he had to run. Thank you for a very nice discussion. Next time, we'll have a presentation by Josh Angrist, who will talk about simple and credible value-added estimation using centralized school assignment. We're all looking forward to that. Thank you all for joining, and hope you have a nice week. See you all next time. Thank you.
A great talk.